In this lesson, we're going to talk about a new type of test called ANOVA, which stands for the analysis of variance. And when we use this test, we use what's called the F distribution, which is new to us. And the F distribution, you can see it displayed here. Just like student T distribution, the shape depends on the degrees of freedom. And for the F distribution, we have two different kinds of degrees of freedom, which I'll talk about in a minute. And the higher these degrees of freedoms get, the more that this curve is going to look normal. However, it will never look completely normal because this is a right-skewed graph. Let me show you what I mean. So look over here at our statistics calculator. I'm going to go down and choose F distribution. And see right now, the F distribution is always right skewed, but it starts to look a little bit more normal and more bell-shaped as these degrees of freedom go up, but it will never actually be like the normal curve where it's symmetric because it's always right skewed. I want to stress that. So as you can see right now, we have the degrees of freedom of the numerator. That's the same thing as saying df1, and degrees of freedom 2 for the denominator. And we have 5 and 2. Now, if I increase this, let me try to go to 10, and I'll go to 20. As I increase this, it becomes less skewed, and it becomes closer to being symmetric, but will never be symmetric. Okay, now let me increase it again. Let's say I go to 40, and we'll go 200. As you can see, it gets closer to being symmetric, but it's still right skewed. It's still not quite symmetric. And just like the normal distribution, this tail here will never go below the x-axis. And this as well here on the left tail. Now, I think I mentioned already that the F distribution is continuous, just like the normal distribution and the student T distribution. And just as a quick refresher, the binomial distribution is discrete, where x can take on only countable values. All right, this distribution is made up by taking ratios of the variance between the groups and the variance within the groups. And like I said, key points here, it's always positive and right skewed. The shape depends on the degrees of freedom. And we use this to test variance and to see if the means are the same or if they're different. Now, this test is specifically for when you have more than two groups. So you might have 3 groups or 4 groups or 5 groups, and it's always going to be a right-tailed test because the F distribution is right skewed. So how do we find the numerator degrees of freedom? We take k minus 1, and k is the number of groups. I have it listed here. So if we have 4 groups, I would take 4 minus 1 and get the degrees of freedom of the numerator is 3. The degrees of freedom for the denominator is capital N, which represents all of the data values in the whole set of groups. And we subtract the number of groups. So capital N means all of the values. If I use a lowercase n, that means I'm just looking at the number of values in that particular group or that sample. But capital N means I count all of the values. So in this case, capital N would be 15 if I'm looking at these values here. Little n in all of these cases would be 5. Now, the examples that I have in this lesson, I believe they're all the same value for little n, but I want to make sure that you understand that they don't have to be. I could have 8 values in this group, and I could have 10 in this group, and I could have 3 in this group. So the number of values in each group do not have to be the same. Now, the steps again for hypothesis testing is still the same. We're just going to be using a different distribution. And when we set up our hypothesis, our null hypothesis, we're going to assume that all the group means are equal. So in this case here, I have three groups, so my null hypothesis would be that M1 is equal to M2 is equal to M3, because these are the mu's that represent the mean of the groups. And then the alternative hypothesis would be at least one group has a mean that's different. Okay, let's get into our first example. Now, I already put these values in my spreadsheet, so if you haven't done that, make sure you pause the video and put those values in, and then we'll get started on the example. A transportation researcher compares the travel time in minutes using 3 different commuting options in Boston. We have the T, they could drive, or they could call a cab. And we want to compare these to see if the means are the same or the means are different. So we're going to use alpha as 0.05. Now, in analysis of variance, I have seen 3 alpha levels that are pretty common. As we've been using before, we have 0.05 and 0.01, but I've also seen 0.1. Okay, so in step 1, we're going to set up our null and alternative hypothesis. Since we have 3 groups, we have 3 means, so I'm going to set it up that mu1 is equal to mu2 is equal to mu3. And then the alternative hypothesis is that at least one mean is different. We're using an alpha level of 0.05, and when we do an ANOVA test, it's always right-tailed because our F distribution is right-skewed. Now, to find our test statistic and p-value, there's a little bit of work here. I'm going to go through this step-by-step very slowly so that you can take note. It's similar to what we've been doing before, but we're going to go into a different area in GeoGebra because we're doing multivariable analysis. So you're going to highlight all your data. Now, if I'm going to put one in here on purpose, but I'm going to erase it just so you can see what I mean. Let's say I had a 6 there. When you highlight those values, you need to make sure you include the 6. So if there's blank cells, that's okay. Just make sure you include all of the values. So I'm going to highlight all the values, and then I'm going to choose my histogram button like we usually do. Instead of doing one variable analysis, we're going to do multiple variable analysis. And you'll see the box plots for each group come up. Then you can click on this button here for the statistics. So you can see it's pretty close to being the same thing. We just went into multivariable analysis. Okay, then at the bottom, let me pull this up a little bit. At the bottom, you'll see information is given to you about each group. You'll see for the first group, A1 through A5, the mean, the standard deviation, the 5-number summary, and then this is all the information for the second group in the B column, and then this is all the information for the third group, which is in the third column. Now, to perform ANOVA so that you can get your test statistic and p-value, then you're going to click on this drop-down menu and choose ANOVA. Then you'll see all the information you need down here. It's a little bit squeezed in, I apologize, but I wanted to show both screens at the same time. But here are the degrees of freedom. So between the groups, that's our degrees of freedom of the numerator. And that's when we find the number of groups minus 1. That's the k minus 1. So between the groups is 2 because we have 3 groups, so we have 3 minus 1, which is 2. So I'm going to make a note of that. I made, you can write it 2 different ways. You can write it degrees of freedom of the numerator, or you can write it as degrees of freedom and then number 1. This is 2. And then this one down here is the total number of values and all three groups together, that's the big N, and then you subtract the number of groups. So this has a total in all three groups of 15 values. There's three groups, so I'm going to take 15 minus 3 and get 12. And so that's this degree of freedom right here is the 12. So I'm going to make a note of that too, because we're going to need it here in a little bit. Okay, here's my F test statistic. So my test statistic is 2.381. And then here's my p-value, 0.1346. So there's my p-value. Okay, so we've got all the information we need for step 2. Now for step 3, we need to find the critical value so we can find the boundary for the rejection region. So this is where I'm going to go back. I'm going to close this out. I'm going to go back to my statistics calculator. I'm going to make sure I choose F distribution. And then I'm going to put in my DF1, which was this, K minus 1, 3 minus 1 for 2. And then the degrees of freedom for the denominator, which was 15 minus the number of groups, which is 12. And I'm going to put that in here. So 2 and then 12. Now, because we're doing a right-tailed test, as we always do with ANOVA, always right-tailed test, I'm going to choose the right bracket so I can see the right tail where the cutoff point is going to be. And since this is a 0.05 level of significance, I'm going to put in that I want my area shaded under the graph. This area right here should be 0.05. And what we get is a critical value of 3.8853. So there's my critical value. So to be in this red region, since the F critical is the cutoff point for that, we're going to reject the null hypothesis if the test statistic is greater than that critical value. Now we're not going to reject the null hypothesis if it falls in the blue area. That's our safe zone. That's where the F statistic is less than 3.853. Now, if we look at our test statistic for F, and I labeled it F because we're using the distribution F, just like with the normal distribution, I label it as Z. In the student T distribution, I label it as T. We're now using the label F. Here's my test statistic, 2.381. 2.831 is less than 3.8853, so it's going to fall in this blue zone. So I'm going to say, do not reject the null hypothesis. All right, now let's go to step 4, which is the p-value method. Our p-value is 0.1346, and our alpha level is 0.05. .1346 is greater than 0.05. So because p is greater than, we're going to say again, do not reject the null hypothesis. Now, remember what we're testing. We're testing to see if at least one of these means are different. We're assuming from the start that they're the same, and we're checking to see if at least one is different. Since we are not rejecting the null hypothesis, there is not enough evidence to suggest that at least one mean is different. So I'm going to put that in here. At the 0.05 level of significance, there is not enough evidence to support the claim that the mean times of commute between the types of travel are different. So let's look at the second example. We have a tourism analyst compares the number of visitors at 4 popular summer tourist attractions in Salem, Mass. And we're going to use an alpha level of 0.05. We have the Witch Museum, the House of Seven Gables, Salem Maritime, and the Broad Street Cemetery, which is where the witches were buried. Well, some of them. It's one of the historical cemeteries in Salem. All right, now for step 1, since I see we have 4 groups and we want to compare the mean number of visitors at each of these locations, we're going to use ANOVA. And we have 4 groups, which means we're testing for means. So I'm going to have for the null hypothesis, mu1 is equal to mu2 is equal to mu3 is equal to mu4. We have an alpha level of 0.05. And then the alternative hypothesis, we're just checking to see if at least one of the means are different. And because this is ANOVA and we're using the F distribution, this is going to be right-tailed. So the first thing we need to do is find our test statistic and our p-value. I have my data values already loaded into the spreadsheet view. If you do not have them in there, please pause the video and put them in there so we can continue. Okay, once you have them in there, we want to highlight all of those values. We want to hit the histogram button, but we're going to choose multiple variable analysis when we're doing ANOVA. And we're going to come up with the box plots for the 4 groups. To show the statistics, we hit this button here, the sigma x. And so down below, you can see all the information for each group. So the first group is in the A column, second group is in the B column, etc. And it has the mean, standard deviation, and the 5-number summary. Now, because we want to perform ANOVA, we're going to click on that drop-down menu and choose ANOVA, and then we're going to get another table that shows the degrees of freedom for each, the numerator and the denominator. And then we're going to have our test statistic and our p-value. All right, so, woo, that's a big one. We have a test statistic that's really big. We have 804.5755. Our p-value is super, super small that it rounds to 0. And now we need to find our critical value for F so that we can use the rejection region method in step 3. So the degrees of freedom of the numerator, that is the number of groups minus 1. Since we have 4 groups, our degrees of freedom of the numerator is going to be 3, and we can verify that right here. Now, the degrees of freedom for the numerator, that is the total number of values minus the number of groups. If we look at our table, we have 5 values in each of the 4 groups. And again, it doesn't have to be the same, but it just happens to be that the examples I use have this. But we have 4 groups, and each group has 5 values, so that means we have 20 values in total, which means our big N is 20. And then when we subtract the number of groups we have, 20 minus 4 is 16, and we can verify that here. Degrees of freedom of the denominator is 16. So now we can use this to find our F critical. So I am going to close this out and look at my probability calculator. I'm already on the F distributions from the last example. I'm going to put in that I have 3 for the degrees of freedom of the numerator and 16 for the degrees of freedom for the denominator. I want an alpha level of 0.05. So I want the area under the curve in this wing to be 0.05. And here is my cutoff value. So my critical value is 3.2389. So if we have the test statistic fall in the rejection region, which means it would be greater than our critical value of 3.2389, that's when we would reject, and we would not reject if it falls in the blue area if it's less than the critical value. Because our test statistic is so high, it way surpasses the 3.2389. So we're gonna reject the null hypothesis. Now we're going to use the p-value. I'm going to put in my p-value is 0. My alpha level is 0.05. 0 is certainly less than 0.05. So this tells me again, reject the null hypothesis. So because we are rejecting the null hypothesis, there is enough evidence to support the claim that at least one mean is different. So I'm going to state at the 0.05 level of significance, there is enough evidence to support the claim that there is a difference between the mean number of visitors for each tourist attraction. Okay, looking at example 3, I already have my data preloaded in there. So if you need to load them in, please pause the video and take a moment to get that set up so we can continue. Example 3 says, an education researcher compares graduation rates as percentages among Somerville High School, Cambridge Region Latin, and Boston Central Catholic School. And we're going to use an alpha level of 0.01. And just as a reminder, another alpha level that you may see with ANOVA tests, you might see 0.1 instead of 0.01. So be aware of that. All right, so we have 3 groups here. So we're going to assume that all of these means are the same, and then we're going to test if they're different. So the null hypothesis is that mu1 is equal to mu2 is equal to mu3. We're going to use a level of significance, 6.01, and because this is ANOVA, it's right-tailed. So in step 2, we need to find the test statistic and the p-value. So to do that, I highlight my data, I choose the histogram button, and I choose multi-variable analysis. And that's where we get our graphs of the box plot for each of the groups. Now I want to see the statistics, so I click on the sigma x, and so you can see all the information for each group below. And then I'm going to use this drop-down menu and choose ANOVA. So we have our degrees of freedom 2 and 15. Let's verify that that's true. So we have 3 groups. So the degrees of freedom for the numerator is the number of groups minus 1. So that's 2, that works. And then the degrees of freedom of the denominator are all the values added up. That's the big N. And we subtract the number of groups. So we have 6 values in each group. We have 3 groups, so that's 18 total values. And then I subtract the number of groups, which is 3, and we get 15. All right. So here's our F test statistic here. It's also, again, a big one, 209.3878. And our p-value, you can see it over here. It's kind of crammed in there, but you can see that it's small enough that it's rounded to 0. So now we need to, in step 3, use the rejection region to make a decision. And so to do that, we need to find that cutoff or that boundary for the rejection region. So we need to find our F critical. So I'm all done with this. I got everything I need from this. I'm going to close it. And we're on the F distribution from the last example. So I just have to change my degrees of freedom. So I have DF1 is 2. And DF2 is 15. And we're doing this at a 0.01 level of significance. So this red area under the curve should be 0.01. So I'm going to put that in here. And I see that my critical value is 6.3589. So to fall in this rejection region, the test statistic must be bigger than 6.3589. So I'm going to put that here. We do not reject the null hypothesis if the test statistic is less than the critical value, because that's where it would fall into the blue value, the safe zone. Okay, so going off of this, when I look at my test statistic, it is certainly much bigger than 6.3589. So this is going to be reject the null hypothesis. Now using our p-value, we get a p-value of 0. And we have an alpha level of 0.01. 0 is less than 0.01. And whenever p is less than the alpha, we say reject the null hypothesis. Because we are rejecting the null hypothesis, we would say there is enough evidence to suggest that at least one of these means are different. So at the 0.01 level of significance, there is enough evidence to support the claim that there is a difference in the graduation between these schools.